Okay, I think we're recording. I think. All right. Well, happy Monday. It's week 3, and we're talking today. The topic is tidy data. Whoops, clicked something. I shouldn't have clicked that. My phone's gonna start ringing now. Stop. That's my. Okay. All right. Well, let's talk about this. Okay. So a couple things. We have a group project for this course, right? So I will start describing what the group project is. So I just want you to start thinking, and maybe you've met some of your classmates, maybe you haven't, but start thinking of making groups of around four people, three to four people is what I want. I don't want to have groups of 5 because then somebody can slip under the radar and do nothing. It's harder to do nothing if you're in a group of 3 or 4, I think. So it's basically going to be a data analysis project. So you'll take a data set and then you'll do some exploratory data analysis, make some charts and graphs, find some summary statistics, ask questions, and maybe and fit a model at the end. And I'll release more details about it as our week goes on. Okay. All right. So today's topic is tidy data and reshaping tables. This is based off of chapter 6 and a few other kind of resources. Just kind of the idea about tidy data here. Okay. Let me get your attention here. As you go and online and you look for data, you're going to realize there's a lot of messy data out there. Okay, a lot of data that's kind of poor quality, a lot of data that requires cleanup or what we might call data wrangling. And as far as analysis goes, as far as analyzing your data and doing work with it, the ideal format is what we call tidy data. Some people might say this is an opinion, but I think it's true, okay? And when your data is tidy, what we want is every row to contain one observation, okay? And every observation should be contained entirely within one row, okay? You don't want one observation spanning across multiple rows. You don't want one row to contain multiple observations, or a case, what we might call it, okay? Same idea with columns and variables. Each column represents a variable. Each variable appears only in one column. And then every cell in your table is just one value. That's what we want, okay? So here's an example. This is from the textbook. This data is not tidy. It says City of Minneapolis Statistics, General Election, November 5th, 2013. And what do we see? Okay, this is like an Excel file, spreadsheet. We've got ward, precinct, voters registering by absentee, total registrations, voters at polls, absentee voters, total ballots cast, etc. So those columns look fine. Okay, those columns look fine. But what we notice is as we go down the columns, we get these rows. Okay, we have citywide totals, Ward 1 subtotal, Ward 2 subtotal. These things mess it up. Okay, with the inclusion of these rows, which is handy when you're trying to summarize stuff and present it to a boss or something. These subtotal rows, however, make the data not tidy and difficult for analysis later. Okay, so what we'd have to do is we'd have to remove row 15, row 27, row 4 also, and pretty much any other kind of row where it doesn't fit kind of the rest of the data there. Okay. When we look at these columns, okay, we've got a couple types of variables, okay? We've got categorical variables, we've got quantitative variables, okay? Categorical variables tell us what type of variable or what type of value something is, or some kind of category. They often take the form of a word, but not always, okay? Quantitative variables record a numeric attribute. They tell us a quantity, how much or how many, okay? Variables like zip code or area code, they look like numbers, but they are actually categorical variables, okay? So, because the area code of your phone number, that does not correspond to a quantity. It doesn't tell you how much or how many. And so it doesn't make sense to say Joe who has area code 818 has more area code than Jane, area code 562. That kind of comparison doesn't make sense, right? If it's a quantity, you can make comparative statements, right? Joe is 2 years older than Jane, right? You're looking at numeric age. Joe is 22, Jane is 20. You can say 2 years age difference. You can say, talk about two people having a weight difference, right? If somebody weighs more than the other person, somebody is this many inches taller than the other person, okay? Somebody has this much more money than the other person. Those are all quantitative variables when you can make a quantitative comparison. But if it doesn't make sense to say, I have more area code than you, okay? That's because there's no quantity associated with that. All right, so look back here. Are any of these variables categorical, or are they all quantitative?
They are.
The leftmost row is categorical.
So which one's categorical?
On the row A.
Row A, column A, ward is categorical. Ward and precinct are categorical, okay? The other ones, they all represent a quantity. How many registered absentee, how many registrations, how many voters, how many absentee voters, how many ballots cast. Those all represent quantities. And you can talk about there were more voters in Ward 2 than there were at, whatever, right? More registrations in Ward 2 than there were registrations in Ward 1. You can make those kinds of things. But in talking about, say, the precinct, is precinct 9 more than precinct 3? It's not. It's just a number, right? It's just a numeric code that doesn't represent a quantity. Okay. So this page really kind of emphasizes the fact that when you have something that's categorical, it might be recorded as a number, but you have to treat it as a category, right? Another example is you could have something like hair color. And, maybe hair colors, we say there's brown hair, black hair, blonde hair, red hair, other color hair, something, you kind of list off these categorical descriptions, but maybe when you record them, it gets recorded as, hair category 3 and hair category 2 and hair category 1 and stuff like that. Again, those numbers, maybe they're recorded as numbers in your table, they correspond to categories, and those numbers don't actually have a numeric meaning. It doesn't make sense to say this person with blonde hair has more hair color than this person with brown hair or something like that, okay? And it would be a big mistake, okay? It would be a big mistake to treat numeric codes as if they were numeric values, okay? It would be meaningless to take the mean of the hair color number. Okay. Similarly, it would be meaningless to take the average precinct. Okay, so a lot of times you see numbers and you say, oh, we can calculate the mean, we can calculate some average. But if we're talking about a precinct, you can't calculate the average there. It doesn't make sense. What's the average zip code in the United States? That doesn't make sense. Okay, is there meaning there? You have a question?
I mean, if you put like black hair is 1, brown hair is 2, and blonde hair is 3, and you get the mean, if the number is higher, couldn't you say like the average hair color is like lighter?
So what you're talking about is what we call an ordinal variable, and if you say, okay, white hair, and now you're transitioning to something where like the number corresponds to something that we can turn into a quantity. perhaps like a grayscale value, right? So if we're talking about like how much brightness or darkness, how much pigment goes into it, right? And so we turn into, like if you look at the hair, there's like melanin, and that's what gives hair its color and stuff. And you can perhaps say you can turn it in, you can take something like hair color and say, quantity of melanin per, centimeter or something like that, and turn it into something like that, and that would represent something numeric. So you could. So certain categorical variables do have a natural ordering. So if you go from like white to, like platinum blonde to blonde to, I don't know what the next name of the hair color, right? Light brown, medium brown, dark brown, black, something like that. Sure, you can make some kind of gradient, but effectively, that's what you have. But then red hair would be kind of on its own separate thing, and I don't know. Certain categorical variables can be put in a natural ordering. Something like never, rarely, sometimes, always type of questions. Strongly disagree, neutral, agree, strongly agree. Those have a natural ordering, and those, we would call those ordinal variables. And sure, you can kind of treat them like numeric variables in some cases, but it's also a little bit dangerous to do so because like numerically, the distance between 5 and 6 is the same distance as the distance between 2 and 3, whereas is the difference between never and sometimes, or never and rarely, the same distance as rarely and sometimes, and is that the same distance as sometimes and always? And it's like a weird question. It doesn't quite work out. So it's a little bit harder there. Okay. You can also take a numeric variable and you can turn it into a categorical one. So you can take something like age, which we often treat as numeric, but you can turn it into something like a minor, someone under the age of 18, and an adult, someone who's older than 18, perhaps. Or, on YouTube, they categorize your age, right? They say, are you 13 to 17, 18 to 25, or 18 to 24, 25 to 49, and 50 to 65, or something. They have these different age groups for kind of targeting advertisements to you. Okay. As far as what the case is, exactly what counts as a case could vary from one table to another. And one important rule is that when you have a table, each row is the same kind of case. You don't want to be mixing different kinds of cases within the same table here. Okay. Let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter E. E as in elephant. E as in elephant. Okay, so this is kind of like a cleaned up version of this table, right? So this is kind of the election values. And what we did is we removed kind of these subtotal rows, and we have something like this, right? We have Ward 1, Precinct 1, registered number, voters, absentee, total turnout, et cetera, et cetera. So this is kind of what we get after we make it tidy, okay? What does each row represent? Each row represents a different ward precinct of the city, okay? So you've got, different wards, and I think within the wards you have different precincts. So, and you would need both the ward and the precinct to uniquely identify a row. Okay. Because precinct 1 exists both within ward 1 and ward 2. So you can't just say precinct 1, you gotta say ward 1, precinct 1 type of thing. Okay. In this table, here we have individual ballots. Each case is an individual ballot that was cast, okay? And so it says in precinct 4, ward 6, they the vote was undervote, undervote, undervote. Apparently, I guess you could do a first choice and second choice. It seems like they had a ranked choice voting, and so this person voted Bob Fine, then Mark Andrew, and then left it, no choice there. Okay, and so here, each ballot cast is a case, right? And so it's the data is coming kind of from the same event, but depending on the table that we're looking at, what is a case? What does each row represent? It's going to be different, okay? And here, when we do a Ward 1 subtotal, this could be a case, okay, in a separate table, right? We could have another table where each row represents an entire ward, okay? If each row represents an entire ward, then this row would fit in, okay? And row 27 would fit in, okay? But we can't, the problem with here is, here we got rows that represent a precinct within a ward, and we have a row that represents the ward entirely, okay? So we don't want to be mixing those two types of things in the same data set. Is that good? Okay. All right, so look at this data, okay? This is an excerpt of runners' performances over time in a 10-mile race. So, you can participate in a 10-mile race. We have Jane Poole, 1948, female, age 55, year 2003, and I don't know what this means. 92.7 gun, is that?
How fast they ran?
I don't know. Is that like when they crossed the starting line? Because I think when you have a big race, everybody doesn't start at the exact same moment, right? You have the crowd. They shoot the gun and the clock starts, but then your race time doesn't start until like you in the crowd crosses the starting thing, and I think that's kind of your like starting time, and then they take your finish time, and then they take the difference to calculate your race time. I think that's how it works, but something like that, right? Because if you think about a marathon where I'm right. Okay, all right. Thank you for confirming that. Okay, so if you think about a huge marathon, you've got a huge crowd. It's not like the 100-meter dash where everybody has the exact moment where they start. You got the front runners and then the people in the back, and so the people in the back might not cross the starting line until like 5-10 minutes into the race or something. So I think that's what the gun time is. Well, anyway, just the question: what is a case in this table? What is the case? Consult with your neighbor. What do you think?
What do you want us to?
What is the case? How would you describe the case in this table? What is the unit, the observation?
The time the racer took the 10-mile race over the 100.
Yeah, I guess how fast.
But
How fast each racer ran 10-mile race.
over a period.
Okay, all right, okay. We have some. So I'm hearing some answers here. Okay. Well, okay. Let's somebody just shout out what you guys think the case, the observational unit, the case is in this table. Runner's performance over time. So again, what is one row here? So all right, is a runner a case? A runner is not a case. A runner's name and their year of birth is not a case because that does not uniquely identify a row. Okay? If I say Jane Poole, which Jane Poole? Oh, the one born in 1948. Okay, I know who you're talking about. Does that uniquely identify the row? It does not, right? Yeah. Yeah, it would be the name plus the year that they competed. Okay, we need both of those information to correctly identify. So it was Jane Poole, and then we, and it's funny, we got this year of birth. So I guess it's kind of just like to uniquely identify the person, right? Like, oh, which Jane Poole are you talking about? I'm talking about the one born in 1948. Okay. And then we can't just say her race time. We'd say which race? She ran like 6 times, okay? Or 5 times. You say, okay, no, Jane Poole, when she ran in 2005, then we can start talking about what happened during that race, okay? And we can compare what happened in 2005 to what happened in 2003. We can compare that to Jane Schultz in 2005 and things like that. So we need both the year and the person's name. That would be the case. Okay? Yeah, question.
So what do you mean? So a case is how we can identify a role?
Kind of, yeah. Each row, so you have to think, how do you identify a row, or what does each row represent? Now, there might not be enough to correctly identify the row either, right? So maybe for privacy reasons, we remove the name column, okay? Now we don't really have a way to identify the row, okay? But we can say this and this represents an individual person that competed during this year, okay? And we can talk about that, yeah.
Will the name and age work?
What?
The name and age.
Name and age?
Will it work?
I suppose it could work. Name and age. Jane Poole when she was 55. It's a little bit of a stranger way to identify something, right? Because it could be like, what? But yeah, that could work. That would uniquely identify the thing, right? And you'd be like, I want to compare. Don't compare me to Jane Schultz in 2005, because in 2005 she was only 41. So I want to, let me know when she's also 55, and then we'll start talking. I don't know, something kind of silly like that. But yeah, you need both of those things to kind of correctly identify. Okay, let's talk about reshaping data. So this data would be tidy, okay? This data is tidy. We would actually not need to reshape this. Here we have each row represent a different storm, okay? So you guys, I think, already analyzed this data set or something, right? We looked at hurricanes and wind speed and air pressure, and you saw the relationship there. And so anyway, that data set is tidy. Each row represents one kind of tropical storm or hurricane. Each column is a different variable, okay? So the different variables that I've shown here, we have the storm name, the wind speed, the air pressure, the date of the storm, one column for each variable. So that's fine. Okay. This is an example of some data that I would argue is not tidy. Everybody can kind of argue that a lot of data sets, as long as you got like one number in each thing and each row represents a different thing, maybe it's tidy just in different forms. But I would say, what are the variables that we have represented here? So this is, I think these are fictional numbers, but like cases of a disease within a country during a certain year, okay? And DE represents Germany, okay, for Deutschland, not Denmark or something, okay? So you have France, Germany, the United States, the number of cases of some disease in 2011, 2012, and 2013. Okay, what would you say the different variables are that we have here? Country is one of the variables.
Years.
The year, and the third one, the number of cases, right? So you've got the country, the year in which we recorded the data, and kind of the case count, okay? And the case count is kind of spread. So we don't have one column for each variable, which is, one of the variable forms column headings, and then the values are spread out across the columns, okay? someone could argue that this is tidy, as it is. But perhaps there's another form that we could use, okay? What do we have here? We've got, so this is the amount of particles. I guess you got large particles and small particles. How many micrograms per cubic meter if you kind of count out the way the particles in the air. And so we looked at New York, London, and Beijing. And so let's say each city was a different case. What are the variables we have here?
City name?
Okay, so city name is one of the variables, yeah, and that kind of would identify each case. Yeah. Yeah, particle. Yeah, so we could argue that this is tidy as it is. That we got particle size as a variable, and the amount of particles is another variable. That argument could be made. I would say, perhaps we could rearrange the data in such a way that, we really just have New York, London, and Beijing, and then we'll have a column for the amount of large particles and a column for the amount of small particles. And the amount of large particles, currently as it stands, exists in one column, and the amount of small particles also exists in the same column. And so what we have to do is we'd have to kind of untangle these things to do that, okay? And what we want to do is we want to reshape this data. So these are kind of these toy data sets that I've loaded up in here. I think we're going to have a separate lecture on loading data into R, okay? So far, all of the data that we've been talking about, you've just kind of loaded using a library, right? We just say like library, MDSR, data this, or, it's all been there. But a lot of times you're going to have to load your own data sets, and so that will be kind of our next lecture where we do this, okay? Now, when you have tidy data, we can do what's called a vectorized operation, which is you can just take two columns and do calculations based on them, right? So if you wanted to calculate the ratio between air pressure divided by wind speed, I don't know what that means. I'm not a meteorologist. I don't know the significance of these things. But we could say, all right, what kind of values do we get? Now, we could just we can refer to each column using the $sign. And so I could use a mutate, or I could just kind of also create a new column. So here I can say, create a new column, storms ratio. So this adds the ratio column here. And I can say, we're going to define this as the pressure column divided by the wind speed column, okay? I could also do a mutate operation. I could do mutate storms, comma, ratio equals pressure divided by wind, right? So these would be just kind of ways to do this. And basically, it just takes each value here. 1007 divided by 110, 9.15. 1009 divided by 45, 22.4. And it does this row by row. For each row, it calculates a new thing, right? So basically, I'm just doing a mutate operation here. And we can do this when you have tidy data. If your data is not tidy, this kind of stuff is hard to work with. Okay. Here is the cases table. The cases table. All right. So again, I've got France, Germany, U.S. 2011, 2012, 2013. Okay. Now, R does not like when your variable names start with a number. Okay. They expect all of your variable names to start with a letter. And so if you want something that starts with a number, if you load it in a data set where the column has a thing, it's going to put in these backticks. It's going to put in these quote marks around it in order to kind of be able to handle it. Or sometimes it might put the letter X in front of it. So I think you saw that when you do your homework this week in the baseball data set. The original data set has like the number of hits, the number of doubles, which would be the batter got second base, the number of triples, and And normally it's just recorded as 2b and 3b, but in the data set, it puts an x in front of it, and it says x2b, x3b, because it doesn't like variable names that start with numbers. Okay, so I want you to think about this. If we make this tidy, what will be the dimensions of the resulting data if we make this tidy?
Change the years to just year.
Yeah. I want you to think about this, talk about this. Talk to your neighbor about how many rows will you end up having, how many columns will you end up having.
So every row represents one observation, and every column I guess we can have like
Oh, is there two variables there?
three, maybe country, year, and the cases.
Oh.
Yes. Maybe we need like three columns, and not rows for each observation.
Okay. How many columns and how many rows? Yeah. 9 rows, 3 columns. That's what I came up with. All right. So when we do this, our new columns will be country, year, and the count, or the cases, number of cases, and we would have a row for each. What's the case? Each case would be a year country combination. Okay, a country year combination would be what each row represents, and we have a total of 9 of those things. Okay, we have France in 2011, Germany in 2011, the U.S. in 2011, France in 2012, Germany in 2012, U.S. in 2012, so on and so forth. And so when we reshape this data, we would end up getting 9 rows and 3 columns. Okay. Do you guys come up with this? Did everyone come up with this, or is this a surprise a little bit? So this operation, transforming basically a 3 by 4 table, 3 rows, 4 columns. Oh, by the way, when we list off the dimensions, it's always the number of rows by the number of columns. Okay, that's kind of the standard notation here. Yeah, question?
Why exactly is that tidy?
Yeah, I mean, so one could argue, I guess it depends. What operation is it that you're trying to accomplish here, okay? So depending on what we're trying to accomplish, we might prefer it in this form. We might, in some cases, we might prefer it in this form, okay, depending on what it is. But if we defined the variables this way, the country, the year, and the count, then this is what the tidy form would be, okay? If this would be, the variables are the country, the cases in 2011, the cases in 2012, the cases in 2013. We would have 4 variables there, okay? The country, the number of cases in 2011, the number of cases in 2012, and the number of cases in 2013, okay? So anyway, this is how we would do it. This operation is called pivoting the data. Okay, we're pivoting the data, and because the resulting table is longer, we call this a pivot longer operation. Okay, so we're taking the data, and we are basically, it's the same data. We're not manipulating the data. We're not mutating it. We're not recalculating anything. We're just calling it a pivot. Okay, because it's just the same thing, but we're just kind of reshaping it a little bit, okay? And because the resulting table in general ends up longer than the original table, we call this pivot longer, okay? This operation used to be called gather, but they renamed it to pivot longer. And basically what we're doing is we are combining the values in columns 2011, 2012, and 2013 into a single column, okay? So we're gonna say pivot longer, the cases table. Which columns are we going to pivot? Which columns get turned from multiple columns down into one column? Okay, it's columns 2011 to 2013. Whoops. All right, and then the names of those columns, the 2011, 2012, 2013, those names get put into a new column that we're going to call year, and the values get put into a new column that we're going to call cases. So we're going to have country, year, and cases. And the results looks like this. We get a 9x3, tibble or resulting thing. Let me give you your second view quiz answer. Second view quiz answer is the letter C. C as in cat. C as in cat is your second view quiz answer for today. C. So this is the pivot longer operation. Okay. So again, a few arguments that we take in. Okay. So these columns. This is the data that you're going to pivot, right? The columns, the values inside those columns, 2011, 2013, those are the ones that get pivoted, okay? And you can specify a range of columns using the colon operator, okay? Otherwise, you can just also provide kind of a vector. You can say, I want these columns. But a lot of times, the columns will be adjacent to each other, so you just kind of give it your starting column name, colon, ending column name, and it'll just kind of do everything in between. The names too is just whatever you want to call, you know, those column headings and they go into a thing. It's whatever you want to call it. It's an arbitrary thing. It doesn't actually have meaning. Same thing with values too. What is the name that goes there? Okay. So, you know, the names are arbitrary. This would be a terrible name, by the way. But if you wanted to call the column when it happened and values to how many, you can do it. Okay. R doesn't care. It's just going to say, all right, I will do what you want, and you can do that, and it will create column names based on whatever you enter here, okay? Generally, if you can keep your columns short and simple without spaces and stuff in there, that's much better, okay? If you need to put a space between things, use an underscore. Use an underscore. Okay. What would happen if I make a mistake and I only pivot columns 2012 and 2013? How many rows, how many columns would I end up having? I'm going to just pivot columns 2012, 2013. What do you think? I won't get an error. I won't get an error. It's able to do this. How many rows do you think I'll get?
6.
We'll get 6 rows, okay. And what will my resulting columns be? So I'm creating new columns, years and cases.
Would it just be the same without the 2011 cases?
So watch what happens, okay? When we do this, the columns I don't pivot just get duplicated, okay? So R doesn't know that country has like significance, like more meaning than the column 2011. This just sees it as data and values. It doesn't care. So it's just gonna, anything you don't pivot, it just duplicates, right? So now I've pivoted the columns for 2012, 2013. We get 2012, we get 2013, 2012, 2013, 2012, 2013, and we get France, France, Germany, Germany, US, US. And then the same numbers, all the values in 2011, just like the values for country name, get duplicated. So it'd be like France, 7,000, and then the year and the cases, right? It'd be kind of like, what if this original table had country, capital, something else, right? Some other piece of information. R doesn't know, it doesn't care. It just sees it, okay, here's a column. It's not being pivoted. I should just duplicate it everywhere, right? So it'll say like France, Paris, et cetera, et cetera, et cetera. You know, Germany, Berlin, blah, 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 US, Washington, blah, blah, blah. And it's just going to duplicate all of that information. So if you don't pivot a column, it just gets duplicated. Yeah?
Under that, so like, what are the names to and values to like represent this?
It's just whatever you put here. I put year, this just becomes the name of this column. Whatever you put here just becomes the name of this column. So we're taking the values in the 2012 and 2013 column, and the values go into a new column called cases. These names, 2012 and 2013, they end up in a column called year. Okay, and it's arbitrary. You can call it whatever you want. Okay, I think year and cases make sense. Maybe year and n, year and count. Those would all make sense. Yeah.
So like, how does like the names to know to represent to like each single rows or like variables?
Wait,
I'm a bit confused. Like how does transformation happen? By using the names to and just get a year on it?
How does the transformation happen?
Yes.
So, wait. I'm sorry. Maybe I don't understand the question. So here are the values, right? 6,900 and 7,000. Okay. Well, let's go back to the original. Or does this make sense? And the other one doesn't? Or so basically, what we're doing is we're taking the original is France 7,000 in 2011, 6,900 in 2012, and 7,000 in 2013. We want to preserve all of this information. Okay.
Yeah.
And another way of presenting this is I could say France in 2011 had 7,000. France in 2012 had 6,900. France in 2013 had 7,000. Okay? And then I can look at this. Germany in 2011 had 5,800. Germany in 2012 had 6,000. Germany in 2013 had 6,200. Okay? Germany in 2011 had 5,800. Germany in 2012 had 6,000. Germany in 2013 had 6,200. It's the same information. It's just being presented in a kind of another format, okay? And all we're doing is we're pivoting the data that currently exists across 3 columns. We're pivoting it so these data exist in just 1 column, okay? I actually put these in the wrong order, huh? I put France, Germany, U.S., and it's France, 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 Germany, 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 U.S., U.S., U.S. Okay. Does that kind of make sense? Yeah.
So say if you want an even longer table, you just do more names to and values to.
Well, there's only one names to column and there's only one
Okay.
values to. Okay,
You can only do one.
you can only do one at a time. Now, if you have multiple things that you want to pivot, right? We had like, let's say you had you might have different tables or something to kind of pivot these things. So, okay, so anyway, this is what happens if you only pivot those 2 columns. Okay, what if I pivoted country itself? What would happen here? What if I said pivot everything? Pivot the country and 2011, 2012 through 2013. I'm pivoting all 4 columns. This would be a mistake. You shouldn't do this. But it's not wrong. How many resulting columns will I end up having? I will have 2 columns. 1 column for name and 1 column for value. And how many rows will I end up having? I will have 12. Okay? So if I do this, okay. First of all, it gives me an error. Okay? It says you got these numbers over here and you got letters over there. I can't combine them. Okay? So first it gives me this, right? It says you can't combine type double, which is a number, with type character. Okay? So I'm gonna just force it. I'm gonna just say treat everything like letters. Okay? So I'm gonna just apply as character. It turns everything into characters and then pivot. Okay, now look what happens. I get country FR 2011 7,000, 2012 6,900, 2013 7,000. Country DE. So it just took all of the things, all 12 values, right? Right now they're arranged in this 3x4 grid. It took all 12 values and just put them into a single column. And everything that used to be a column heading got put into this thing named. Yeah. Does this represent what?
Is this how they represent sparse matrices?
Sparse matrices?
They have some position, almost the value of that position.
Yeah, so a sparse matrix could be represented this way in that you have you got 1 column for X position, 1 column for Y position, and then 1 column for the value. Yeah, rather than putting it into a a grid. So it is kind of pivoting that with also just and then. So you could think of, let's say you have a 1,000 by 1,000 matrix, okay? So what it would do is it would pivot everything into this X and Y position, and basically it becomes 1,000,000 rows, right? You got 1,000 rows and 1,000 columns, and it's gonna have every single thing, 1,000,000 rows with basically X position, Y position value, X position, Y position value. And then it saves space by saying, well, everything's a 0, throw it away, right? So sparse matrix. So it only makes sense if you only have a few values that aren't 0, okay? Otherwise, now you got 1,000,000 rows and 3 columns, which is generally not going to be more efficient than the 1,000 by 1,000. But if only a few values have values, then yes, the sparse matrix can save you some space by doing the X and Y position rather than the thing. Yeah. Okay. Well, all right. Let's see. So this is kind of the reverse situation. So it's kind of like the values now are in one column, and there's also kind of the key, large, small, large 23, small 14, large 22, small 16. And what I want to do is I want to pivot it wider. Okay? So if I pivot this wider, how many rows will I end up having? How many columns will I end up having? I want to have a column for large particles, a column for small particles. How many rows should I end up having?
3 rows, 3 rows, and 4 columns.
3 rows and 3 columns. Okay, right now I have 6 rows and 3 columns. When I pivot it wider, I'm going to get 3 rows and 3 columns. We're going to get 1 row for each city, 1 column for the large, 1 column for the small.
Oh, that's a lot more organized.
Huh?
That's a lot more organized.
I mean, it depends on what you're trying to accomplish, whether you want, right? What are you trying to accomplish? And depending on the form, one could be more suited for the other. Okay, so this seems pretty good. Okay, so this is what we call pivot wider. We take the names, right? So it's kind of the opposite, right? Names 2, values 2 was in pivot longer. Here we're going to say, hey, take the names for the columns from the size column. Take the values that fill in those things, take that from the amount column. Okay, so it's going to say names from and values from. Okay, and you can see it's kind of like a reverse operation, right, of the pivot longer. Pivot wider is the opposite. It's going to say, hey, take the values in this, take the names in this column and make it the names of your columns. Take the values in this column and put them in the values for the thing. Okay, so we've got the names from and values from. And that's pretty much it, okay? So, okay, let me give you your last view quiz answer, and then I got a couple examples of just like things that could go wrong, okay? Last view quiz answer is A as an apple. A as an apple. Okay, so here, I got a city. New York has been abbreviated NYC, New York City. What's going to happen? I'm going to do names from size, values from amount. Same thing that we had before. How many rows am I going to end up having? I'm going to end up having 4 rows. Okay? I'm going to have a row for NYC and a row for New York. And it's going to fill in NA values for where the value, kind of the matchup didn't exist. So I have NYC large is 23. I don't have an NYC small anywhere in this table. I have a New York small 14. I don't have a New York large anywhere in this table. So I end up getting 4 rows, 3 columns. Okay. This one, what you can do if you end up something like that, so this would have been a mistake, but you can also say, hey, I don't want you to put in NAs, put in zeros, okay? And you can put in a fill quantity, values fill. If you end up in a situation where you're going to have you can't find it, just put in a 0 or some other arbitrary number. Okay, what if I spell large with all caps in this first row? Large, all caps, okay? How many columns am I going to end up having? Yeah, so we're taking the names from the size. Now I have 3 unique spellings in the size. I got a small, I've got a lowercase large, I got a capital large. And we're going to get columns for each of those things. Okay, we're going to have New York large, New York small, New York large. And then we've got London. There's nothing for all caps large. Beijing, there's nothing for all caps large there. Okay, so when you do this pivot wider business, it's very important that you have a consistent naming scheme in that size column, right? Somebody spells it with capital letters and someone uses lowercase letters. You're gonna run into issues like this, right? And so when you run into issues like this, you go, I got to clean up this column, right? And maybe it takes some manual work to do it, and that's the annoying part, especially when you're like scraping data off the internet and nobody knows how to write things consistently. You end up in situations like that. Okay, let me see what else I have here. All right, so this is just to say pivot longer and pivot wider are the same thing. So I could do pivot wider here, and then if I wanted to, I can take the operation and pivot longer back to the original form. And I'll just say this, that they are kind of inverse operations here. Okay, we'll end here for today. We'll see you guys on Wednesday. Have a good day, and have a good week 3. We'll see you guys in a couple of days.